Welcome to my mad scientist laboratory where I rigorously test the DeWALT 20 volt max portable power station. Bear with me while I move my tripod around because it's going to be a little awkward at times. You wouldn't believe it if you saw my ridiculous setup. It's pretty hokey. So I got a lot of things going on here. I got the power station all set up with a extension cord splitter so that I can connect as many devices as I want. Here I have a lamp, just a normal table lamp with right now that's an LED bulb in there, and it's a weird type of LED bulb, but it is an LED bulb. Then I have an old style three-way incandescent down here, and then I have a CFL. Next I have a kettle here. This is a 1500 watt Secura like electric kettle for boiling water. Down here I've got two cups of water, and then over here, even cooler, I've got a kilowatt meter, and I've been using this a lot with this power station, and I found out some really interesting things which are going to come up a bit later in the video. But for now, so this goes to the wall. Damn it, hard to tilt. So this cord just goes straight to the wall, and then there's a on-off switch right here. Interesting feature. You wouldn't have noticed this unless you could hear it, but when I just turned the power on there to the power supply, it automatically turned off the inverter, which was running. So that's kind of an interesting feature. As people have noted at various times online, you can't charge the batteries and use the inverter at the same time, which is really interesting to me. I don't know why that is. My cat's trying to get into my bag of CFL light bulbs. But anyway, yeah, so let's conduct some tests here. The first one I'm going to do, since I got one request to actually show this power station powering some devices, this one's the most interesting to me, is the electric kettle, which for some reason already had water, because it's high wattage, and you'll actually get to hear the fan kick on. So I think it takes about 2 minutes normally with wall power to do the kettle from cold to boiling, with like room temperature. I'm gonna do something a little extra here, and I'm gonna plug the kilowatt into the power supply here, so we can actually get an idea of how much energy this kettle is using. So let's see, can you see that? Yeah, okay, so these are really cool. I totally suggest anybody at all just get one of these kilowatts, because they're so cool in educating yourself about how your devices consume power. So right now it's on the volt setting, which is this button right here. So it's putting out 116 volts, which is kind of interesting because it's like normally your wall outlet's supposed to have like 110 to 120, I think, is like the range. So it's like a right in between. Well, not right in between, but like a little over 110 amps. Right now it's outputting 0.1 amps. It's fluctuating a little, which is kind of interesting. Like, why is it outputting 100 what are those milliamps? 100 milliamps? I think that's right. Either that or 10 milliamps. I'm not sure. So okay, watts. It's not putting out any watts right now. Hertz. Oh, look at this. This is cool because this is where you actually get to see the modified square wave inverter in action. And in my previous video I made a mistake, and for some reason I wrote down 120 hertz on the whiteboard, but wall power in the US is supposed to be at 60 hertz. So you can see it's fluctuating 55, 45, 50, 48. It's like really erratic. It's very dirty power. If I just plug this straight into the wall, and which you'll get to see later, it'll just pretty much be at a solid 60 hertz, which is what it's supposed to be. This button is my favorite. So this meter button tells you how many kilowatt hours of power your devices are using. So it's just like a little power meter that you can actually like, when you get power from the power company, it's like sold to you in kilowatt hours. I think for me, it's like 14 or 18 cents for every kilowatt hour. So you can tell like exactly how much money any device is costing you with this. Okay, so I'm gonna flip it on, and then I'm gonna systematically go through the buttons and end up back here on the kilowatt hour. So here we go. All right, so right away the inversion sound of the power station immediately just disappeared, because this kettle's using pretty much all the available power, like pretty close, to the 1800 watts of continuous power. So it's using all but 300 watts, and you can hear that fan. It's loud. Like that's the power supply fan, like way on the other side of the power station. Pretty loud, huh? So let's see, we got 110 volts it's sucking. Let's see how many amps we got. 11 amps, 11.4 amps of power it's sucking. 100, oh wow, 1200, yeah, so that's almost right on. So 1238 watts approximately. 1240 watts. So pretty close to the well, not really, actually not close to the 1500 that it says on the kettle that it actually is supposed to be. But look at this, the inverter is kicking out power to really solid 60 hertz. That's really impressive. Like, look at, there's no fluctuation at all. 60.1. That's like pretty amazing. So here's the actual meter, and look at that. It's already up to 0.03 kilowatt hours. So still a fairly infinitesimal amount of consumption, but pretty cool. I'm fascinated by this right here. Like, this is really curious to me. I think it might have something to do with the fact that the power station is more or less maxed out for output, that it's so stable. Because with other devices that I've tested, this has not been stable. So that really intrigues me. So yeah, this is taking a couple minutes. And my other test with this kettle, it's taken a little bit longer to boil water with the power station than from the wall, which is logical, because the modified sine wave is less efficient, like up to 30% less efficient than regular 60 hertz wall power. So it's possible that it's just less efficient. Okay, so let's see. So yeah, so 0.05 kilowatt hours to boil that water. And like, that was a little bit more than 2 minutes, I think. Not sure exactly. Alright, so that kind of concludes the kettle test. I'm just going to move right on to the light bulb test. Wow, that's a little bit hot. So I'm going to unplug the kettle. Really a pain to move everything around with just one hand. We'll be right back. Okay, so I'm gonna unplug the kilowatt to reset it. Okay, Now I'm plugging it back in, and the count's gonna start again. So yeah, fluctuation, major fluctuation in the hertz. Still drawing that amp, 0.1 amps. Okay, so I'm gonna connect the lamp. Okay, so trying to make it so everything's visible here, so it doesn't look like I'm doing some sleight of hand or some shit. But all right, so this is an LED bulb. It's a weird one, but it's an actual LED bulb. So I'm gonna turn it on, and this is really cool. I wanted to show this one first because you can actually see the fluctuation of the hertz. And like here, check this out. This is interesting. Let me untwist this so I can get it a little closer. So if you look at the hertz now, it's very variable. It's not regular. It's fluctuating a lot, like up to almost 20 hertz of fluctuation. Well, average it out to about 10 hertz, but that's pretty crazy. And you can't see this because it's not, my camera's not adapting to the light, but with my eyes I can actually see the like pulsing fluctuation in the filaments themselves. So that's kind of cool to actually be able to see the variance in the dirty power. Okay, watts. So this is like 115 watts, or no wait, volts, sorry. 115 volts, duh. 0.1 amps draw. Virtually no watts. That's kind of weird. I would have expected something to show up on there, because it is producing light, so that's kind of confusing to me. I don't really understand why that is. Okay, let's switch bulbs. Oh, nice and cool, because it's an LED. It's like ice cold. CFL next. So I'm just gonna go down the efficiency chain here. So this is kind of interesting because right away, like the oh, that's cool. So you're actually okay. So the reason it wasn't showing anything in the watts readout is probably because it was so low that it was like next to nothing. It was pretty much zero. So the device, or the kilowatt, didn't even register it. But this CFL, because it's a lot less efficient, is using about 10 to 15 watts of electricity to produce that light. Kind of a cool thing here, you'll probably notice this, like, this one's pretty much instant on. This is a very high quality, expensive, natural light CFL. So I think it's got really high quality circuitry inside, which is why it just instantly comes on. The other ones I've tested, there's been a little delay and kind of an uneven lighting, which I think is also due to the hertz. So look at this, fascinating. Once again, it's pulling off a miracle of a consistent 60 hertz. Like, why? It's really interesting. I think it must have something to do with the electronics in the CFL somehow. I don't know. Your guess is as good as mine. Let's see. Yeah, so 13, 15, 18, 16 watts, 0.7 amps, 0.67, 0.7 amps approximately. Okay, so that's the CFL. Pretty cool. We're gonna try the incandescent now. Finally, this is pretty hot. I could burn myself if I just kept holding on to this bulb. All right, here we go. This is actually a 3-way bulb, and the highest level of brightness is 150 watts. So Let's see what we got here. Oh yeah, this is cool too. This is another example where you can literally, well, you probably can't see it in the camera, but I can see it with my eyes. The filament is actually vibrating in there. Not a lot, but just enough to actually be visible. So let's see what we got here. Hertz. Okay, so here we have the more or less consistent 60 hertz again. So far the CFL and the incandescent have had consistent draw, but oh wow, it's dipping now. So it's got some kind of weird fluctuation in there. But it looks like it's very regular. 45, 50, 40, 50, 60, 40. I don't know. It's a mystery. I really don't understand the fluctuations in the hertz. So let's see, 80, 82 watts, 79, 80. So about 80 watts, which is interesting. So it must be on like the 100 watt setting instead of the 150, like the middle range, because this bulb goes up to 150. So this is just basically a 100 watt bulb right now in the lamp. And it's using about 80 watts, 0.7 amps. I'm actually really curious now to know like how many watts of draw are necessary to kick on the fan for the inverter. I'm guessing it's fairly high because that kettle is so far the only thing that I've actually noticed triggering the that fan. Okay, so I'm done with this for now. I'm gonna unplug the lamp and get this out of here because I wanna bring over a power tool and see how that goes, because as everybody knows, electric motors are like kind of a big deal when it comes to the reliability of the modified square wave. Yeah, so check this out. I'm actually kind of proud of this because I picked it up at a swap meet a few months ago. It's a vintage, like, brand name skill saw. Let's see, it's a 10 amp. Wow, 10 amp. Don't know how many watts. I could do the math to figure that out, but 10 amps. So let's see, this thing has a max output of 15 amps. So we're really going to be kind of putting it through its paces with this skill saw here. Alright, and this is definitely going to be loud. I'm curious to see if the fan's going to kick on with this. Okay, so I'm resetting the kilowatt so that I can get good metrics. Okay, so you're probably not going to be able to hear me talking when I turn this on, so I'm just going to turn it on for a second, see a little bit longer in a second, see how long it takes for the power station's fan to turn on, if at all. So the band didn't kick on at all. I noticed the motor did seem a little bit like rougher than normal outlet usage. So I'm gonna just guess that has to do with the hertz, but I don't know for a fact. I'm gonna actually attempt to do something a little dangerous here and hold the kilowatt while I use the saw. Yeah, so it was using like 6 amps, and it says that it's 10 amps, so that was like 4 amps short. But obviously, if you're cutting a board, it's gonna be putting more wear on the, or stress on the motor, and then it'll draw more amps. So I feel like that's probably just within tolerances. So that's pretty cool. So far I've done like a kettle, like a thermal load. I've done a light actuator, 3 different bulbs. I've done an actual brush motor, which, if you notice, a kind of a cool thing about this old style saw, it doesn't have an electric brake. The blade just keeps turning even after the power button is flipped. So yeah, that's, I think, a pretty good sampling of devices that the power station can run. I did have one incident the other day that was kind of unfortunate. I hooked up an LED novelty bulb and ran it for a few hours, and a capacitor inside actually exploded, which I'm gonna go get that really quick so you can see, because it's kind of cool. Yeah, so this is like a bargain basement, super cheap ass Chinese capacitor metal film. So the fact that it fried is probably not that anomalous all by itself. I think it just, the dirty power from the modified square wave inverter probably just kicked it over the edge and caused it to fail. So that was kind of cool, like a good lesson to learn. Um, okay, so I had one other thing that I wanted to go over, which is charging, which I forgot to go over the other day when I made the other video. So I'm gonna just move things around a little bit here. Okay, so kilowatt. Right. Okay, so I'm hooking the kilowatt up to the wall. I'm plugging in the power charging part of the thing. I'm gonna flip the switch, and this is nice because you get to see how the LEDs work. Right now they're flashing. They're flashing red on the left side, and that means the batteries are charging. And when they're fully charged, they will just turn solid red. These other LEDs on the right side are for like hot battery, low batteries, other like notifications essentially. Oh yeah, so this is what I wanted to show, which is that it's charging, right? So it's normal that it would be drawing power because it's charging. So it's drawing 2.3 amps, like rock solid. Look at that, 2.31 amps. 182 watts. So that's a lot of power, really. 180 watts. Since this is wall power, you're getting to see the actual, like, this is how it should look when you get a perfect sine wave power supplied to you by like your power company. 59.9, rock solid, never fluctuates. That's like picture perfect wall power hertz right there. So how long does it take to charge these batteries from 0 to full capacity, 6 amp hours? For all 4 of them, and they do, even though it's a parallel charging station, I've noticed they do actually charge in sequence. Usually this is the first one that is fully charged, and it takes 4 hours approximately to charge all 24 amp hours. So all the batteries are fully charged from 0 in about 4 hours, which is really fast and pretty impressive from my point of view. Right, what else did I want to go over? Right, okay, so now, even though I drained the batteries, so they're not all fully charged, so it's still charging them, but I did a lot of tests on this last night after I'd fully charged everything. And the interesting thing about this power station is that even when the batteries are fully charged, it still draws power, and not an insignificant amount. So I told you it takes 4 hours to charge all these batteries, but it also takes about 0.48 or 0.45 kilowatt hours of electricity to fully charge all the batteries. So that was an interesting metric, because using that you can figure out like how much it costs to charge the which, let's see, that's about 9 cents really to charge, because power is so ridiculously cheap. So it only cost me like 9 cents to fully charge the 24 amp hours. Your power company rates could be totally different, so it might be a different expense for you. But what I wanted to say was that even when everything's fully charged, the power station still draws power when it's plugged in, and like I was saying, a fairly significant amount. So it's drawing 2.3 amps right now when it's charging, but it's still drawing power. I think it was like 0.1 amps when it was fully charged, and it was drawing like 5 watts. I can't remember. I really wish that I'd done this before I depleted the batteries a little. But what I'm getting at is that it's not something that you just plug in and forget about, because it is actually drawing power even when it's not charging, when it's just sitting there plugged into the wall. So that's kind of something to think about, because it's costing you money to just have it sitting there being plugged in. So you probably want to unplug it after it's fully charged. That would be my recommendation. Yeah, so I think what I'm going to do actually is pause the video, pause the recording, wait till it's fully charged, and then show you the kilowatt hour readings, the kilowatt readings, so that you can see how much power it uses when it's just sitting there fully charged. Alright, having thought about this a little bit more, I don't think it's going to work out, because I don't know how long it's going to take to charge, and my phone might go to sleep and I might lose all the video. So I might just do a short video sometime in the future showing the power draw while it's dormant. Yeah, anyway, so hopefully this kind of supplements the other video and provides more useful information. And thanks for commenting and giving me some like suggestions and feedback so that I could make this follow-up video. It was really helpful. And yeah, thanks for watching.